11.1 Parabolas. As we saw, parabolic mirrors focus incoming rays of light on a single point. This is a fundamental property of the parabola, and the point is itself called the focus. The focus has a companion which lies behind the parabola's arc, a straight line called the directrix. Together, these two form the original geometric definition of a parabola given in the text on page 724. The description here interprets the definition. Description. For any point P on the parabola, the distance from P to the focus is the same as the distance from P to the directrix. To see an animation of this and to see it traced across the full path of a parabola, click on the YouTube link here. 1. The curve of the parabola passes directly between the focus and the directrix. Given this, what is special about the vertex in relation to the focus and the directrix? Well, let's sketch what we did just above, but in a slightly larger form. So here we've got the focus, and here we have the directrix. The vertex for this parabola is living here. Vertex. Now, what's notable about the vertex is that the vertex has the shortest distance on the parabola to both the focus and to the directrix. So shortest distance of any point on the parabola to both focus and directrix. And in fact, this distance is so significant that we label it. We call the distance P. So we have a length of P from here to here, and we have a length of P from here to here. Next, let's use this p-value and the rest of the propositions of our description to derive the equation of a parabola with the vertex at the origin. We're going to use the focus and the directrix to achieve this. So, for an arbitrary point on my parabola, we'll pick one this time out over here. I've got some coordinates, x and y, and that's a distance, and that's also a distance. And we know that those two distances are the same. Now, what are the coordinates of our focus? Remember, our focus lies right here. Well, the coordinates of the focus, we said that the height right there was length p. So that would imply that the focus has coordinates 0 on the x and p on the y. Similarly, we had the same distance down to the directrix. That's also p. That'll come into play in a moment here. Okay, so we have one point xy. And we have another point 0, p. And we want to find the distance between these 2 points. Remember what we said about the parabola was it has the same value of distance from here to here as it does from here to here. So we can use the distance formula. What the distance formula says is that my first length here should have the following measure. It should be x minus 0 quantity squared plus y minus p quantity squared. So that would be this distance. And it needs to be equal to this distance right here. So let's get that distance. Well, we again have 2 points. We know that we're going down to the directrix. And we know that if we were to look at this point, it's got the same x-coordinate as our point up on the parabola. So it would be at x. And the y-coordinate here is negative p because we have dropped, remember we've dropped p units below the x-axis. So for my other distance, I would have x minus x quantity squared plus y minus a negative p quantity squared. Now we just have to do a little bit of simplification. We're going to have x squared plus y minus p squared. That's going to be equal to, well, x minus x is 0, so we can eliminate it from the conversation. And y minus a negative p is y plus p quantity squared. Y plus p squared and the square root of that. We should be able to drop our square roots at this stage. So we can say that x squared plus y minus p squared equals y plus p squared. We're going to expand. We'll get y squared minus 2yp equals y squared, oops, missed, y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. A little scrunch there. And going through and eliminating terms that are in common on both sides, my y squareds go away, my p squareds go away, and if I shift the negative 2yp over, I'm going to get x squared equals 4yp. And mathematicians conventionally express this as x squared equals 4py. Remember, p is my distance from the vertex to the directrix, which is the same as from the vertex to the focus. So here we have the parabola with vertical axis. The equation of a parabola with the vertex at the origin and a vertical axis of symmetry is given by x squared equals 4py. For such a parabola, the vertex is at the point 0, 0, so vertex at the origin. The focus, now the focus will always be p units above the vertex. So the focus will always be at 0, p. And the directrix will always be p units below. So the directrix will always be y equals negative p. Now, it's important to note that these values would hold if our vertex was, if our parabola was opening up or opening down. But what is it that determines whether the parabola opens up or down? Well, it might be helpful at this stage to do a little bit of a rewrite. If we were to solve for y and say we're going to take x squared equals 4py and do the shuffle that we would expect and get that y equals 1 over 4p times x squared. What would determine whether the parabola opens up or down is whether p itself is positive or negative. So the negativity of p determines up or down opening. So let's try using this definition. Find the equation of a parabola with the vertex at 0, 0 and the focus at 0, 2. Okay, based on what we said above, this means that our p-value is equal to 2. So we could get away with simply saying that the equation would be x squared equals 4 times 2y, which is to say x squared equals 8y, y equals 1/8 x squared. And if we were to think about the sketch of that, that's a very broad parabola. So a focus at 2 and a directrix down below would be something like that. Now, find the focus and the directrix for the parabola y equals negative x squared, then sketch the graph. Well, we know that this has the form y equals 1 over 4p times x squared. So if we have negative x squared, that means that negative 1 must equal 1 over 4p, because 1 over 4p would have to be that leading coefficient. So let's solve for p. So this would mean p equals negative 1/4. So this is very, very tight. And it tells us that we are opening down. So if we were to sketch, because we're opening down, I'm going to do more on this side. Let's say that this is 1, this is negative 1, negative 1 and positive 1. There's a half, and there's a 1/4. So my focus is going to be at 0, negative 1/4, right there. My directrix is going to be y equals, we said negative p, right? So negative 1/4, so y equals 1/4, which is to say it's that line up there. And what that tells us is that our vertex, right, is right in between the two. And there is our parabola, roughly speaking. Now, we can also talk about parabolas with a horizontal axis. The equation of a parabola with the vertex at the origin and a shouldn't be vertical axis of symmetry, it should be horizontal axis of symmetry is given by y squared equals 4px. In this case, our vertex is still 0, 0, but our focus will now be p for the x coordinate, 0 for the y, and the directrix will be x equals negative p. Okay, what determines whether the parabola opens right or left? You may have guessed that it is again the negativity of p. And specifically, when p is less than 0, we open left. We would open towards the negative x-axis. A parabola has the equation 6x plus y squared equals 0. Find the focus and directrix of the parabola and sketch the graph. Sketch the graph by hand, then use a graphing utility to check your work. So let's go ahead and isolate our variable. We're going to say that 6x equals negative y squared, which gives us x equals negative 1/6 y squared. So that means that negative 1/6 equals 1 over 4p. Let's double check ourselves on that. No. I am messing it up. Back out. Okay. So if we've got 6x equals negative y squared, we can simply isolate the y and say that negative 6x equals y squared. So now we are matching our formulation up here, which means that negative 6 equals 4p. Yes, this is better. So then p equals negative 3/2. Yeah, great. So negative p, that means we're opening to the left. We're still centered at the origin, so that makes our lives a little bit easier. We're opening to the left, so we'll have something like this, and we just need to figure out the curvature and how that plays. So let's get our p, our directrix and our focus in place. If p is negative 3/2, then that means that if this was 1 and this is 2, that my focus lives right there. And by extension, my directrix, so my directrix will be a positive line. It'll be x equals 3/2. It'll be the exact opposite side. Okay. So this is a reasonably large p-value, so we will have a pretty shallow parabola in play here. And we said, let's try to graph this with a graphing utility. So let's go take a look at it on Desmos. 6x plus y squared equals 0. And what do you know? There we have it. The beauty of Desmos and GeoGebra and these other utilities is that they handle what are called implicit graphs very easily. You don't have to be able to write a graph as a function. the calculators are pickier about having graphs centered as functions. The web-based utilities are way happier to see things like 6x plus y squared. Last topic, focal diameter. The focal diameter is the length of the line segment that passes through the focus parallel to the directrix, spanning the parabola edge to edge. The focal diameter will always have the measurement for p. So what does this mean? If we wanted to visualize it, focal diameter would be that length there. Too many dotted lines, if you ask me. We'll get rid of it on this figure. Let's sketch ourselves another parabola. This time we'll do it vertically so we can see that it still exists. Focal diameter is going to be a line length in red. There's my focal diameter. Distance from there to there. And as we said, total measurement for absolute value of 4p. Determine the focal diameter of the parabola in problem 4. Okay, so we had a p-value of -3/2, referencing back there. We know that the focal diameter will be the absolute value of 4 times p. So this would give us a focal diameter of absolute value of -6, which is just 6.